Okay, we're going to go ahead and see, with 5 questions, 4 choices each, something that looks like this, the probability that exactly 3 are correct. Okay, so what's going on here? What we're going to do is we're going to go ahead and look at each question as a different sample, right? So these are different events. So the first, and then sequentially. Okay, so what's the probability that randomly guessing we get this first question correct? Well, you can see if there are 4 choices. Again, if we have no idea, it's equally likely, right? So we have a 1 out of 4 chance of getting this thing correct. Or if you'd rather, you can convert that to 0.25. So our probability of getting this thing correct, so this would be our success, is 0.25. And that's what we're interested in, exactly 3 correct. So how many do we get correct? Correct is 0.25. And for this one, again, it might not be the same answer, but there's only one answer. There's 4 choices, so I have 1 out of 4, is 0.25. For each question, I have a 25% chance of getting it correct. So my P is 0.25. A little bit more, we should see, okay, these things are Bernoulli trials. Are we doing binomial trials? Or are we doing a geometric sort of thing? Now, let's see. The number of trials is fixed. We have n is equal to 5. Okay? And we want exactly 3 correct. So we're not saying get the last one correct. There are just 3 correct. It could be any of these 3. So we want our x to be 3 or k, depending on how you decide to write this thing out. So yes, we do want to use the binomial distribution. So let's see, the probability that we get 3 correct is x equals 3 given this thing. So they write it as this, n take k, or n take x, I suppose. I'll write that. P to the x, and q to the n minus x. So filling this stuff in, we got 5 total. We want to take 3. And P is 0.25. We've got X is 3. Q is going to be the complement of P, 0.25. Probability of a failure is 1 minus 0.25. Gives us 0.75. And if these 3 were successes, it must mean there are 2 that are failures. Gives us our 5 trials. Or you could plug in 5 minus 3 to give you 2. That works too. 5 minus 3 gives you 2. So we want to go ahead and compute this thing. Let's look at 5 take 3. Recall that's 5 factorial over 5 minus 3 factorial times 3 factorial. So this is 5 times 4 times 3 times 2 times 1 all over 2 factorial here, right? And 3 times 2 times 1. So we have, this will cancel with that, this will cancel with that, 3 cancels with 3. And so we have 20 on the top, divided by 2 factorial, which is 2 times 1, that's just 2. So 20 divided by 2 gives us 10. So if I'm going to continue off of here, this is going to be 10. Make it clear that I'm not using this, this is just off to the side. 10 times 0.25 cube it times 0.75 square it. Let's see what this gives us. 0.25 cubed gives us 0.015625 times 0.75 squared, and then times 10. So this whole thing equals 0.0879. And that's the probability of getting exactly 3 correct. Same situation here. 5 questions, 4 choices. So this tells me, yes, I'm talking about something that's binomial for the same reasons that we discussed the first one. It's the same situation, so of course this is binomial. Exactly 3 or exactly 4. Well, what this means, we can use this property of sums here. So we can rewrite this as what? The probability of exactly 3 plus the probability of getting exactly 4. And you see that these things are mutually exclusive. Normally, this is the point where we would subtract off the probability of the intersection, but there is no intersection, so that would be 0. So that's why we don't have it. So the probability of exactly 3, we did that on the last problem. We found that was 0.0879. So plus the probability that we have exactly 4. So really, all that's left to do is find the probability that we get exactly 4 of these 5 questions correctly and add it to this previous probability. So just a refresher, our probability of getting each question correct is 0.25. That means our Q is 1 minus 0.25, which is 0.75. N is 5. And X here is going to be 4. That's what we're interested in. So the probability that X equals 4 is precisely this. Again, we'll use the formula n take x times p to the x times q to the n minus x. And let's go ahead and plug this stuff in. N, of course, was 5. X was 4. P was 0.25 to the x, which was 4. And then q, 0.75 to the 5 minus 4, which is just 1. Okay. So 5 take 4, let's do this out to the side again. This is 5 factorial all over 5 minus 4 factorial times 4 factorial. So this is 5 times 4 times 3 times 2 times 1 all over 5 minus 4 is 1 factorial. And then 4 factorial, if I write that as 4 times 3 times 2 times 1. So I get a lot of cancellation here. 2 with 2, 3 over 3 is 1, 4 over 4 is 1. So I have 5 over 1 factorial, and 1 factorial is 1. So this thing is just 5. Continuing on, what does this equal? So that, of course, was 5 times 0.25 to the 4th times 0.75. We get 0.25 raised to the 4th is actually 0.0039. And then we're going to go ahead and multiply that by 0.75, and then, of course, times 5. So this gives us 0.0146. So back to what we were doing, we had the probability of exactly 3 from the last problem. Probability of exactly 4 is 0.0146. So what we were asked to find is just add these two together, right? So once we do that, plus 0.0879, we do get 0.1025, or approximately 0.1. We have 75 routers. Average price that we had sampled was $55. The standard deviation is $15. So we want to know the variability in the means of these sample size of size 25 or 75. So really we want to go ahead and find the standard deviation of this mean. So again, remember, we're talking about the standard error of this mean. So what do we really have? Remember, this is standard deviation divided by the square root of n. This is the standard error for a mean. From there, we just plug everything in, right? So it's just standard deviation was 15, all divided by the square root of n. And here is 75. We have 75 of these things. So of course, it's just 15 divided by the square root of 75. So this is 15 divided by 8.66, approximately. And dividing this thing out, I should get about 1.732. So that means that the standard error is precisely this. So we don't have variance here. This is precisely the standard deviation. There's no need to take the square root of this. Standard error is in the units that we want it to be. So we're given that 1,500 students took this exam. The median is 74, the mean is 70, and the standard deviation is 8. Find the probability that a student chosen at random scored above a 75 using the normal distribution. So we want precisely this, the probability that X is above 75, that our one student has scored above a 75. Okay, so we do this in the normal routine. We go ahead and find the z-score here. The z-score, of course, is what we observe. So what we observe minus the mean, all divided by the standard error. So in this case, what we observe is 75. The mean here is 70. So we subtract off 70 and divide by the standard error. Well, the standard error of one student, we found of these 1,500 students, the standard error here was 8. So it's just this sigma. So you do this calculation, you get 75 minus 70, of course, is 5 over 8. So this is the z-score, so we have this kind of notion. We want really the probability that standard normal random variable is above 5 divided by 8. Or if you'd rather, we can go ahead and divide this out, get an actual fraction. 0.625. But of course we won't use 0.625, right? We'll use 0.63. We'll round this thing. That way, we can actually find it in our table. Our table only goes up to the hundredths, right? So that's why we round this thing. And just to give you an idea, we want this thing to be above 0.63. So if you're going to just find 0.63 positive, which you would have, that would give you this white area, and so you would have to do 1 minus this white area. Of course, you don't have to do that. In actuality, you could just say, well, this thing is symmetrical. So I could say, okay, well, if I found negative 0.63 over here, this area is the same as this area. So you can just look up negative 0.63 in the table, and that will give you what you want, because this thing is symmetrical. Give me a second to open up to the page. Alright, so let's see. The negative 0.60123 is 0.2643. So 0.2643. So this is that probability that we're looking for then. So we have sort of a similar situation. We have these 1,500 students with this mean, median, and mode. We're told that this is normal distribution, so we can go ahead and proceed from there. We want to know the probability of taking a sample of 80 students, 80 of these 1,500 students, and seeing the probability that that average is above 71. So this is slightly different. We're looking for the probability that their average is above 71. Okay, so normally we have this z-score. You have what you observe minus the mean, all divided by the standard error. Well, the standard error of what you observe. So what we observed, we're trying to find the probability of this thing being greater than 71, right? So let's look at 71. Minus our average. Our mean was 70. So we minus 70 all over the standard error. But the standard error for x bar is not just the standard deviation. On the last problem, one student, this is what is given to us. We're actually interested in the standard deviation divided by the square root of n. So once I actually proceed here, my z is 71 minus 70, that's just 1, all over the standard error. Well, this thing is 8 divided by the square root of how many people did we have? So we're talking about this sample here. So we've got a sample of 80. So we're going to go ahead and put 80 in there. So we'll go ahead and proceeding in that fashion. Square root of 80 gives us 8.944. When we do 8 divided by that thing, we get 0.894. And doing 1 divided by that, we finally see that, yes, our z-score is 1.118. Let's round to the 1.12. Okay, so now this is equivalent to finding the probability that your standard normal variable is greater than 1.12. Nothing changes here, right? You use the same direction and signs. So we'll go ahead and use our table again. So just keep in mind what's going on here. We got this 0 here, 1, 2. So we want to know the probability that actually lies above 1.12. So we want this area. Just like on the last problem, you could look up 1.12. You'd have to do 1 minus the value that your table gives you. Or you could use negative 1.12 because you know this thing is symmetrical. And then you don't have to do any of the subtraction. So negative 1.12 is 0.1314. But I lost 0.1314. So our probability is 13.14%.